The last reaction in this chapter is called the Wittig reaction. And the Wittig reaction produces alkenes from aldehydes or ketones. And the way that it does this is by the use of what's called an ylid. An ylid. Now, what is an ylid? Well, you make ylids by taking triphenylphosphine, so PH3 triphenylphosphine, and reacting it with an alkyl halide. That alkyl halide could be a primary alkyl halide or a secondary alkyl halide, but it cannot be a tertiary alkyl halide because there has to be a hydrogen coming off of the carbon in order to form the ylid. So this is important to understand. And what happens is in the first step you get a nucleophilic substitution reaction, chloride comes off, and you generate this species. So now the phosphorus has a positive charge on it, right? And this is called a phosphonium ion. Now, if we take that phosphonium ion and we treat it with a strong base like an organolithium reagent, right? So if I treat it with butyllithium, that butyllithium can remove a proton from the carbon attached to that phosphorus. And if we think about it, that phosphorus is electron deficient, so it's withdrawing electron density away from the carbon, and it makes that carbon-hydrogen bond fairly acidic. So what happens is that we still need a strong base like organolithium, and it will remove that proton, and it generates um, this species, right, where the phosphorus has a positive charge, the carbon has a negative charge on it, and the pair of electrons reside on that carbon. Now, obviously, we can draw a resonance structure of that. If I donate that those electrons in between the carbon phosphorus and create a double bond, now I have a neutral complex. And oftentimes you'll see this written both ways, but this is called an ylid, right? An ylid, where you have triphenyl phosphine connected to a carbanion. Um, but there are these two resonance structures, and you'll see both of them written. Typically, as reagents, you'll see it written kind of like the way on the right, where you have that double bond between phosphorus and carbon. So ylids undergo 2+2 cyclization reactions with carbonyl compounds. If I take an aldehyde or a ketone and I treat it with an ylid, and I'm drawing it this way to denote those pair of electrons on carbon. If we think about what's taking place here, that carbon is nucleophilic and the phosphorus is electrophilic. So the carbon can donate a pair of electrons to the carbonyl carbon, and the carbon-oxygen bond breaks, and those electrons go to the phosphorus. And we produce a cyclic structure that looks like this, right? And so you see, whatever carbonyl we start with, aldehyde or ketone, the two R groups are coming off. I'm showing the ylid having a hydrogen and some R group, but it could also have two R groups coming off. It doesn't necessarily have to be a hydrogen and an R group. And this is what's called an oxophosphatane. And that oxophosphatane is relatively unstable. You can think about, the angle strain on this 4-atom ring here. And so what happens is the bond between phosphorus and carbon collapses, and the electrons go to in between that carbon-carbon bond. And at the same time, the carbon-oxygen bond breaks, and those electrons go to form an oxygen-phosphorus bond. The result is now I've generated a new carbon-carbon double bond, a pi bond, and I've also generated an oxygen-phosphorus pi bond, right? But the key is to note that I produced an alkene from a carbonyl and an ylid, right? So the carbonyl reacts with an ylid to produce alkenes. And this is very reminiscent of what we've seen throughout this chapter of nucleophiles attacking attacking the carbonyl at, at the carbon, and electrophiles attacking the carbonyl at the oxygen. So this is kind of the best of both worlds here in this particular reaction. A couple of examples I'll show you. Here I take benzaldehyde, treat it with my ylide. So notice I'm showing it with that phosphorus carbon double bond. And so the key to figuring out what the product is going to be is, in essence, you take that carbon phosphorus double bond and you're pretty much replacing the carbon oxygen bond with the double bond of the carbon and whatever group is coming off of that carbon. Notice in this example there are two hydrogens, and so we produce a terminal alkene this way. So that CH2 group is at the end of, and we've just basically converted the carbonyl into a carbon-carbon double bond. Here's another example where I have cyclopentanone and I'm reacting it with an ylide, a cyclic ylide. So again, what am I going to do? I'm going to take the carbon-oxygen bond, I'm basically going to break it, and I'm going to add the carbon-carbon double bond, and the result looks like this. And that is how you make alkenes from ylides and carbonyls. And this is called a Wittig reaction, and it's an excellent way of making very bulky alkenes that are typically a little bit harder to make.